Welcome back. We'll be going into chapter 12.4 from textbook page 34. We'll be looking at general motion, which is curvilinear motion, looking at general and rectangular component. Rectangular component is mostly at 3D, three-dimensional. So we'll be describing the motion of particle traveling along the curved path, and then we'll be looking at the terms kinematic quantities in terms of rectangular, the 3D part. So the application, the path motion of this plane itself can be tracked in the XYZ coordinate relative to the point to the earth, recorded as a function of time. So like what I've told you earlier, we looked at linear movement. We looked at linear movement earlier, right? So linear movement is S, V and A. Now we are looking at curvilinear movement. So in curvilinear movement, we have R, V and A. And A, we have got two types of A. I'm going to explain that A shortly. A and A T. Two types of A. Okay, we'll come to that later. Now, these are the applications. Now, if you have this example, roller coaster traveling, car travel down in a fixed helical path at a constant speed. How can we determine the position and the acceleration at the instant? So these are the examples that you may need to calculate at. Okay, so general curvilinear motion. So what we have here, a curvilinear path. Can you see this is a path where the particle is actually moving? A curvilinear path. And then we have the position. So the displacement will be given by delta S, but mostly because of vector, it will be called as delta R. For curvilinear, it's always been written as R. So it will be R, V and A. R, V and A. So this is the velocity component. Okay, so this is the velocity component. Can you see that? We have delta R over delta T, and then the instantaneous velocity is time derivative dr over dt. So this is the path, and always remember the velocity is tangential. Okay, the velocity is always tangential. The particulate, can you see the particulate? The velocity is tangential. It's 90 degrees to the path itself, the path. Next we'll be moving on to the acceleration. The acceleration part. So acceleration will be delta V over delta T. Delta V over delta T. The delta V that you have calculated earlier, you divide by the time. Or you can also differentiate dv dt, or you differentiate the R twice. So this is for the instantaneous acceleration. Average you know how to find average, right? Divided by the total time. So the plot of a locus point defined by the arrowhead of the velocity is called the horograph. So this is actually the horograph. Can you see the red line here? The horograph. Okay, so that would be the what you call the locus point. So the acceleration of vector is always tangent to the horograph. Can you see the acceleration? It is tangential. So we have got two acceleration, an and at, like what I've explained earlier. I'm going to go into detail in the couple of slides later. Okay, so now we're going to move on to the rectangular component of the velocity itself. Rectangular component. So like what I've told you, velocity vector is a time derivative of the position, and then the unit vector, remember what we have done in statics, ijk represents axis x, y, z. And then we have the velocity component, which is vx in x-axis, I, vy, j plus vz, k. In magnitude will be square, inverse square root. Okay, square of x, square of y, square of z, inverse square root. Okay, so if you differentiate this, if you differentiate these, you get the acceleration. Can you see this? Ax. If you integrate this, then you will move to the this. Can you see that? So it's like even though it's in x-axis, y-axis and z-axis, you differentiate these, you get velocity. You differentiate this again, you get the acceleration. Yeah, following the root of v, r, v and a. So even though it is in x, y, z axis, you still can apply it. So to find the magnitude, ax square, ay square, az square, square, inverse square root, you get the magnitude. It's applicable to acceleration, velocity, and also position. Yeah. Okay. So as usual, I'm going to skip the example that's given in the textbook. Yeah, example that's given in the lecture note. Yeah, I'm going to go straight to the example that's given in the textbook. Yeah, so let's move on to the textbook. Yeah, this is a nice image. It looks like me, right? Okay, so I just want to say something about this. Yeah, okay, so what we have here is that we have the r, right? Okay, when you differentiate the r, differentiate the r, you get the v. Okay, another way to write the v is actually r dot. Okay, so when you differentiate these twice, you get a. Or another way to write this is v with single dot, or it is actually equivalent to twice of differentiation. You understand how it goes or not? Okay, so it's like r dot or s dot. If you say s dot is actually equivalent to velocity. You understand, nah? Okay, so s double dot actually equivalent to a. Or another way to write a is actually v with single dot. Yeah, similar to this dot here, isn't it? Yeah, looks like me with a dot, right? Okay, just remember that. Yeah. Okay, so now let's move on to 12.9, because we're going to have all these dots here coming up. So that's why I just explained to you that. Yeah. Okay, look at this question. 12.9 is from your textbook, page 39. Yeah, page 39. Now, of course, before you take up this dynamics, yeah, you have to clear your calculus 2. Yeah, where you have studied the chain rules of calculus. Yeah, and it should be concurrent with your calculus 3 subject. Yeah. Okay, let's look at this. At any instant of the horizontal position of the weather balloon in the figure, this figure, so it's defined as x equals to 2t. So the x-axis is defined by 2t with time, but the y-axis is defined by y. Yeah, y equals to x square over 5. Okay, sorry. So x is what? X is 2t. And what is y? Y is x square over 5. So there are two methods in solving this question actually. Yeah, there are two methods. One method is to use the chain rule and to stick to this formula that's given by the textbook itself, which I'm going to do that. Yeah, the second method, can you see my pencil mark here? Yeah, the pencil mark that I've written here. X is actually 2t. Okay, so what is y? Y is, you plug in the x value into this equation, which is 4t square over 5. Okay, so there are two ways in doing this. We are just going to follow the purple mark here. The blue one, you can just try it by yourself at home. Okay, so let's look at this. Vx, remember the x just now with one dot, you differentiate with time, you get 2 meters per second. So keep that aside. So Vx is settled. Next, Vy. Vy is your double y with the single dot, and y is given as x square over 5. Okay, this is where your chain rule comes in. Okay, you solve with your chain rules and you plug in, because the question is actually asking for time at 2 seconds. So you plug in time 2 seconds inside. Okay, you get 3.2. So you have two values now. We have the Vx value and also Vy value. Keep that aside. To find the magnitude, you square the values and you get the magnitude. Okay, settle. Now to find the angle, it's always y over x. So the value of Vy over Vx, you get 58 degrees. So that is the direction. So you have found the magnitude and the direction of the velocity. Now we're going to move on to acceleration. Yeah, acceleration. So what is ax? You just have to take the value of the Vx. You differentiate once, so you get 0. So keep that aside. So ax is 0. Okay. Then we have the ay. Yeah, ay. You use your chain rule Yeah, you can refer to Appendix C of your textbook itself. Yeah, you solve for the chain rule. So, and then you plug in the time with 2 seconds. Yeah, because you see this is 2x dot, right? X dot is actually velocity, and then x double dot is actually acceleration. So you plug in the value of acceleration in the x-axis. Can you see? Is 0. Yeah, this is 0. Yeah, what is the velocity? Velocity will be 2. Vx is actually 2. See, this is x dot is actually equivalent to Vx. So you take the 2. Okay, that's why it's square here. See, square 2 over 5. Here would be 2. What is the it'd be 4. At 2 seconds it'd be 4. How did you get 4? Because x equals 2t. 2 times 2 is 4. And then the 0. What is the 0? That's the acceleration, because ax is actually 0. So you plug it in, you get 1.6. So now you have got your ax and ay. Ax is 0, ay is 1.6. Square it, you get 1.6. Okay, then you can find the tangent. Okay, you get 90 degrees. So this is how you solve the question. Okay, so the purple ink will be the textbook's way of solving this. Yeah, textbook way of solving this, because this is using chain rule. Okay, and then I told you that the blue mark, yeah, the blue mark is the one that you can do at home by yourself, or I can just explain to you here just briefly. Yeah, so x is given as 2t. This is an alternative method. Yeah, the blue mark is actually alternative method. Yeah, so what is y? Y is given as x square over 5. Correct. So it means y, you plug in the x into t, it will be 4 over 5 t square. Okay, so when you differentiate the x, yeah, when you differentiate the x, what do you get? Okay, so x is 2t. When you differentiate the x, you get vx equals to 2. You differentiate the ax, you get what? 0. Okay, keep that aside. Next, with your y. So now your y is 4t square over 5, right? Okay, when you differentiate this, you get what? 8t over 5. When you differentiate this, you get 8 over 5, correct? Okay, now to solve you plug in the time 2 seconds. Yeah, you plug in the time, which is 2 seconds. Yeah, they have told you the time is actually 2 seconds. You take the time, you plug in into here, you will get the same answer. Yeah, so that's the reason why I want you to just redo these questions and understand. If you don't understand, then you look for me during the consultation hours. Yeah, okay, so there's 2 methods that I've explained to you. Now let me just move on to the next one. The homework will be follow the guide. Yeah, the guide has actually told you which questions that you need to actually answer. So next part we'll be moving on to motion of projectile. Yeah, motion of projectile, which is from your textbook page 41. Okay, it is 12.6, chapter 12.6. If you see, why does this textbook starts with chapter 12? Yeah, because this is a continuation from statics textbook. Statics textbook ends at chapter 11, so that's the reason why dynamics starts at chapter 12. Yeah, so students will be able, the objective is students will be able to analyze the free flight of projectile motion. Okay, so let's look at the application. The application is almost quite a number of sports, yeah, using projectile. Yeah, like this one is American football, I guess, or rugby. Yeah, football also, and then what else? Tennis also, badminton also. Whatever that you launch, it goes in a projectile, right? Projectile motion. Yeah, or maybe like this. Yeah, projectile. It always comes up with a projectile motion. Yeah. So we're going to study what is the projectile. So you're playing a netball or basketball, you launch the ball, it goes in a projectile motion. Okay, so it's kind of like important. Yeah, there's daily application. Even the firefighter, can you see, when he shoots the water, it's actually like a projectile. Can you see? It's like curving, and then yeah, that's a projectile motion. Okay, so So it can be treated as two rectilinear motion, one in the horizontal direction experiencing zero acceleration and the other in a vertical direction experiencing constant acceleration. Yeah, I'm just going to explain to you that shortly with some drawing. Yeah, before that, let's look at this unique part of it. Yeah, okay. For illustration, consider two balls on the left. So we have one ball that we dropped, the red ball, yeah, and the yellow ball, both dropped at the same time. Yeah, so notice that both balls are subjected to the same downward acceleration, that's gravity, remain at the same elevation at the same time. Note that the horizontal distance between the successive photos of the yellow ball is constant, since the velocity in the horizontal direction is also constant. In other words, also these two balls will actually arrive at the same time if there is no any other friction or no any other factor. Yeah, as long as it's all both in vacuum, yeah, both same type of material, if they are made of same type of material, same size, same surface area, both will arrive at the same time because they only have the influence of gravity. Okay, so this is the unique part of projectile motion. So let me just explain another one. Okay, before it goes into this kind of complicated thing, let me just explain about projectile motion. So we have like this. Okay, so we have like this, right? So the ball is kicked, it launches, goes to the peak, and then from here it has a downward force. Up here is upward force. So always remember, we always divide them into two parts, which is the x-axis and y-axis. X-axis got nothing to do with y-axis. They are independent of each other. Okay, they are very independent of each other. Why? Because they're perpendicular to each other. This is x, this is y. They're perpendicular to each other. So likewise, when the ball launches from here, it has an initial velocity. Textbook uses v, yeah? V for both, v naught and v. V naught and v. Yeah. So I'm just going to use similar so that you don't get confused. So v naught x, v naught sorry, not v naught anymore. This is v final. Okay, v final, vx, and then we have ax, and then we have time x. So here we have v naught y and vy, and then we have ay, and then we have ty. So like what I've told you, these two are independent of each other. They are independent. Okay, so if you look at this ball here, at this position here, it has got two components. One is the vy, v naught y component, and then this is the vx, v initial x component. Yeah, v initial x component. Like what I've explained to you, we have v naught y component and v naught x component. So both are launching at the same when they launch, both have got value. So the value of vy will be decreasing because at this peak here, you do not have any more vy component because it's not hiking up anymore. You only have a vx component. Now remember, because the acceleration in x direction is 0, so the vx value is always constant. So if it's an 8 here, it will be always 8 no matter where it goes. 8, 8, 8, 8. Even landing here will be 8. But it's not the same case as the vy. No, it's not the same case. Because vy at the peak here, this is the peak. We always take that this is the peak. This is always the peak. Yeah, so vy at the peak is 0. Vx, if let's say this is initially launching at 8, then this will be 8. Up here also will be 8. Doesn't make much difference. Yeah, so vy, let's say it is launching at 10, this component here 10. Yeah, just number. Yeah, so up here it will be 0, and the acceleration will always be the gravity's acceleration. Yeah, because in y direction gravity actually affects, and there is no any acceleration in the x-axis. The only thing that is common between these two is actually the time. When the time taken, yeah, we always consider the initial. This is initial, and this is final. So for a x-axis, it means it's from here to here. Yeah, you may need to multiply twice for the total launch. Multiply twice, yeah, because the time here, you have to, the time here to reach the peak, time here to land back. Okay, so if let's say the time is 20 seconds, the tx will be 20 seconds, ty will, okay, so for it to go halfway through is how much for y direction? It's 10 seconds lah, halfway. Okay, but for the total time that's taken, it will be 20 seconds or so. This is the only thing common that these two is sharing, the time. Otherwise, this and this are very independent of each other. Okay, let's go to the textbook. This drawing is actually given in your textbook itself, similar to what I've actually told you. Can you see v naught x, v naught y, but they're not launching at 0, not launching, is launching at y naught, at a distance of x naught initial and y naught. Okay, the gravity is always in the y direction. We do not have any acceleration in x direction, no acceleration in x direction, no. Okay, v naught y will always be the same. Yeah, vx, it will be always the same. Yeah, can you see this? Since ax is actually 0, the velocity of the horizontal remains constant. So v naught x, vx will always be the same. Okay, so how do you calculate the x distance? So what you can do is that the whole x distance here, you can take the initial v naught x because it's launching from here, right? Okay, so because it's launching from here, but you are taking the whole total x distance, so you take x naught plus velocity here multiplied with the time, so you get the total x. Yeah, why is ax equal to 0? Yeah, why is the ax equal to 0? Why are we taking ax equal to 0? Because there's no acceleration in the x direction. The only thing that's affecting this launch of this particle is actually ay, which is actually direction of the gravity. There's nothing else. Yeah, okay, so if you to write your vx and vy, yeah, you can refer to your textbook page 41, because vx is almost like everything is the same. Yeah, so that's why they have only written the vy here. So vy, v naught and gt. Why are they explaining, why are they like expressing the acceleration in g? Because it's gravity. You can express this way. Yeah, y equals to y naught if it doesn't launch at 0. Yeah, and then v naught times with t. So if you look, this formula is actually same like s equals to ut plus half at square. Remember this formula? Yeah, yeah, similar, right? Yeah, it's just that you now replace everything with y. This is vy. Okay, and then this is gravity. Yeah, it's actually taking from that formula. Yeah, the s equals to ut plus half at square, and then this formula replacing all with vy as well. This is the initial plus 2as. Remember this formula, v equals to u plus 2as. Yeah, now replacing everything with vy, so v initial y, and then this is the gravity. And what is the s? S is the displacement between y to y naught. Yeah, okay, so I've done explaining the formulas. Yeah, so now let me just go in and discuss an example with you. Yeah, so like usual, I will skip the example in the lecture note because the example is a bit easy. Yeah, very easy. You can just read up by yourself. Yeah, and then understand them. It's really very straightforward and easy. Okay, I'm straight going to go to the example that is in the textbook. Yeah, okay, and your homework, you just have to follow the study guide for the homework of what from this chapter. Yeah, okay, let's go to the example. Okay, this is an example from your textbook, which is example 12.11. Yeah, from page 43. Yeah, page 43. So what we have here, a sack slides off the ramp with an horizontal velocity of 12. So horizontal velocity is 12. So what does horizontal velocity say? If it's 12 here, it's 12 everywhere. 12 everywhere. Yeah, so don't, because it doesn't have an acceleration, right? Okay, so it means Vx is 12. V naught x is also 12. V whatever, it's always Ax is how much? 0. Yeah, Ax is 0. And then what do we have with Ay? Ay is your gravity. Yeah, your gravity. 9.81. If the height of the ramp is 6, it doesn't launch with 0, yeah? This is the initial height. Initial height is 6 from the floor. Determine the time needed for the stacks to strike the floor, and the range R, they want the horizontal distance. Yeah, horizontal distance of the thing. Okay, so this is what we have. These are the key points that we have. Okay, let's look at how to solve this question. The origin of the coordinates is established at the beginning of the path. The initial velocity of the sac is VAX 12. So VAY is how much? At this point, the initial y, yeah, we call this VAX because this part is A. So VAY is actually 0. Because it's only having horizontal component here. Okay, there is no vertical move here, because when you launch, it's actually going downward like this, you know. So that's the reason when it's at the peak here, you don't have a vertical component. That's why Vy is always 0 here. Nothing, no nothing, but it's actually starting from the horizontal. Then from here we'll have Vy. Now then here we'll have Vy. Okay, the Vx value is always the same throughout. Okay, always understand that. Yeah, remember that in your mind. So that's the reason why it is Vy equals to 0. Okay, so next. So we have the AY is 9.81. I've just given to you, and then we have taken negative y because the gravity down, we are taking downward as negative, yeah, and we are taking upward as positive. Okay, so what is VBX here? When it launches here, yeah, what is the velocity? So VBX and VAX will be the same, which is 12, because it's given initially, right? 12. So it will be the same. Okay, so what you have to find now, the three unknowns will be VBY, R, and the time. So when you have all this information, you will find that it is useless to actually fit into the x-axis. Yeah, when you fit into the x-axis, you can't solve anything. Yeah, you always have to find for the time in using your y-axis. Yeah, so that's the reason why, can you see they use the formula, which was the formula that I just explained to you just now, but that formula was given in okay, wait, let me just show you the formula that we went through just now, right? Okay, remember this list of formulas? They look similar, right? It's just that they replace these with what do you call? They replace these with YA, distant location B, location A, yeah. With, okay, look that. Okay, here you can see YB, YA, yeah. YA, why? Because initially it's launching at 6 meters. So now the most important here is that where are you going to take your reference? Where are you going to take your reference is so important, because this is vector. Okay, vector. And so you need to find where is the datum. Yeah, where is the datum? Yeah, that's so important in this question. So this question has actually set the A as the reference point. That's the reason why, can you see the YA? YA is actually 0. Okay, that's the reason why YA is 0. Okay, and because it is down 6 meter down, 6 meter down, so what we have here is that because it's 6 meter down, so what we have here is that it's negative 6 meter plus with VAY. What is VAY? Is 0. So put the value inside there. Yeah, 0. Put the value there, 0, and then we have half, we have the gravity, and then we have the time, time that we need to look for. Okay, so this will give you the time as 1.11. So with that time of 1.11, okay, so we have solved which part? They are actually asking for time, right? Okay, so we have solved for time, so done. The second part is to solve for the range, so you take the time, you fit into the x equation, xb equals to xa VAX TB. So plug in the value, you get the R as 13.3. So with this, we have actually ended chapter the second part of the video for chapter 12. We have not ended the chapter, yeah, we have just ended up to chapter 12.6. So please do the questions that has been explained in eLearn, yeah, whatever the questions and the thing. I will see you in the next subchapter shortly. Okay.